We're going to continue with some calculus ideas. This is a little weird. This one is very simple and just intuitively, but in math language kind of lets us down here. So sometimes what we take is something from the real world that it takes several sentences to explain. Math can sum it up very simply. But as we get into more complex ideas, it's more like a logic puzzle. Math language always has to be precise, and so sometimes math language can turn a very simple idea into something that looks like a legal document because it has to make sure it gets it correctly. And that's what happens here with continuity. Continuity is simple. If you had a graph, the question is, at a particular point, does it just keep going? Like it doesn't break anywhere, there's no holes, it's continuous, it just goes on. So like we'd say at x is 4, is this a continuous function? Well, yeah. At 4, we have a function that just keeps going right along. No breaks, nothing like that. However, we could have something that isn't continuous. So we saw this when we had the idea of a discontinuity. So this was a discontinuity here. There's a hole right there in the middle. Now, it is not continuous because we have this break. We could also see one where perhaps we have a jump where it goes between that open hole, it goes right down. So it is not continuous. We have a break in the function. So math language needs three things to be true in order to precisely define continuity. So it's very obvious what it is. The function goes on. But math language has to make this legally binding, I guess. So the first thing is your function has to exist at that point. So if you look at 4 here, does our function exist there? Yes. If it doesn't, well then there's no way that you're going to be continuous because it's got a hole. But now that's not enough. The second thing we need is that we have a limit there. So as I approach from both the left and the right, am I getting the same value? So look here, I'm approaching from the left and I'm approaching from the right, and I have the same value. So is this enough? This one has a limit because the limit from the left and the right are the same. Does this mean continuous? No, because it wasn't defined there. So we need both of these, and we need one more thing. We need not only there to be a limit, not only for the function to exist there, but the limit has to be that precise value. So let me show you quickly here. We go through the value of 4. Yes, the function exists there. As we come from the left and the right, do we have a limit? Yeah, they're both approaching this spot right here. And then lastly, is the limit the same thing as the value of the function there? Yeah, yes, it is. We need all of that just to see if a line doesn't break. That's all of that. Because both of these would fail. It does not have a value at that first one, even though it has a limit. So this one is not continuous. This one is defined at that spot, and it has a limit from the left and the right, but they're not the same limit. So that one doesn't work either. So we need all three conditions. Now I've kind of already hinted at what these are. We have a jump discontinuity if our limit from the right and left are not the same. So we may have limits, but they're not the same from the right and the left. So the function has jumped. And then we can have a removable discontinuity, which we've been talking about in this whole section. I mentioned this one a lot. This is that we were able to factor it out of the equation, but we are not allowed to exist at that spot. So even though it has a limit from the left and the right, it doesn't exist at the value we're interested in. Or it might be possible that it exists, but that's not the same as where the limit was. Okay, a very simple idea that's gotten very complicated. This is again when math kind of lets us down. It makes a simple idea more complicated when we need these very precise definitions. Now, they want us to define these. Are these jump or removable discontinuities? They're pretty easy to tell, but we'll think of it as the conditions, by the definitions. If you factored this down, you would be able to eliminate the x minus 5. So I know this is going to have a removable discontinuity at 5. Remember, you could do x minus 5, x plus 3, and this would cancel out. So you're left with x plus 3. So that's gone. So this is a removable discontinuity. But if you want to do it by the definition, if you put 5 in, this function does not exist. And so that means it cannot be continuous. And that's the definition of a removable discontinuity. It has a limit from the left and the right. We could use this to help us find that. But at the value of 5, it doesn't exist. So it's intuitive to see this is a removable discontinuity, but if we use the definitions, we can prove it as well. Now let's go over here. Now let's go through this is going to be a jump continuity because it's a piecewise function. I can see it's probably going to have a jump involved, but let's talk about it. First of all, does this exist at the value of 2? Here's where the jump is probably at, so I'm going to look at this. Does this exist at 2? No, it doesn't. It doesn't actually exist at 2, so we know it's not continuous. Now, how can I show that it's a jump discontinuity? Well, let's put those values, let's do this place where I think it jumps. Let's put 2 in. Put 2 into this, I get 3. So the point 2, 3. Let's put 2 into this, I get -2. Okay, so from the left, we're approaching 3. From the right, we're approaching -2. So this has got limits from both sides, but they're approaching different locations, so this is a jump discontinuity. All right, now if you think you got it, go ahead and pause it. I'm going to talk us through this here. I'm going to go ahead and get started. I could factor this top down. And so I could instantly see that I'm going to be able to cancel those x minus 6's. This is a jump discontinuity, or this is a removable discontinuity. That's what they are. You could remove them from the equation. But if you were trying to think this through, at the value of 6, this function does not exist. So it cannot be continuous. I'm losing my definitions. Hold on. I've gotten confused on which one I'm supposed to do. So yeah. So all you need is that you have a limit. Yeah, so we have a limit here. So the limit here at any value is just going to be this x. Like we put in 5, it's going to be x. 4. So this has an easy limit. We know how to find this limit. So it has a limit, but it doesn't exist at the value of 6. So this is by definition a removable discontinuity, which I already knew when I started. Okay, now this is piecewise, so I'm already suspecting this is a jump continuity, but let's check it. So if we go through condition 1, do we exist here at, say, 4? This is where the jump seems to happen. Well, yes, I exist here. I would use this top one. Oh, no, I would use this one. Do I exist when x is 4? Yes, I get 8. When x is 4, I get 8. So yes, I exist at 4. Now, is the limit from the left and the right the same thing? Well, at 4, if I put it in, I get the square root of 4, I get 2. No, from the left I'm approaching 2, from the right I'm approaching 8. These are not the same, so it jumps. So it does exist there, but it violates condition 2 because the limit from the left and the right are not the same. Okay, this isn't all that helpful. Now, let's go through. This is what the more typical question is going to be. I don't want to know what kind of discontinuity it is. Typically, the question is it continuous? So let's go through the definition here and try to see if we can reason this out. So again, it's pretty intuitive with the graph, but let's be precise in our math language here as we move into calculus. So at 3, when x is 3, does this exist? Yeah, it does. So you put 3 in here, you get 12. Okay, so it exists there. Okay, so condition 1 is good. Now condition 2, at this value of 3, do we have a limit? Well, when you come from the left, you get 12. When you come from the right, you get 11. So this does not have a limit, and so condition 2 is not satisfied. So this is discontinuous when x is 3. Now let's try it again here for part B. So I've got 4 times 8/3. So 8/3 would be in this one. It would be less than 3, so I'm using this equation to try to talk about what's happening with this function. So 4 times 8/3, I'm going to get 32/3. So yes, the function exists when x is 8/3. Now, how about condition 2? Do we have a limit? Well, if you approach 8/3 from the right or the left, it doesn't matter. This is not going to break. This 4x doesn't have any issues. So to find the limit of a linear equation, all I got to do is put in 8/3. So it isn't the boundary point. I'm not worried about a jump. All I'm doing is checking here, and I get 8/3. So the limit from the left and the right are 8/3. It has a limit at 32. The limit is 32/3. So it exists at 8/3. It has a limit at 8/3. And now the last question, condition 3, is the limit the same as where the function exists? And yeah, they're the same. So this is continuous. I know that's a lot, but that's the world of calculus for you. That's what it's going to be like. Okay, so now feel free to try this one. Pause it if you'd like. Now they just want me to check if this is continuous at x equals 2. So condition 1, does it exist there? Well, when x is 2, we use this top. So yes, 1/2 exists. So condition 1 is good. It does exist. Now let's try condition 2. We need to be coming from we need to have a limit. So from the left and the right, we need to be getting the same value. Well, from the left, we get 1/2. From the right, we get 9 times 2 minus 11.5. We're going to get 18. I'm going to get 6.5, I believe. So from the left, we're approaching 1/2. From the right, we're getting 6.5. These are not the same. This means although they have individual limits, the overall limit does not exist. And so this is not continuous. Condition 2 failed. Okay, now we've got a couple more of these here. Whether or not this is continuous, it's obviously going to be a discontinuity here. We already know that. You could factor this down, get rid of the x minus 5s. So this is going to have a discontinuity and it's not going to work. But let's prove it. If you put 5 into this function, if you put a 5 in there, it's going to make a 0 in the denominator and it doesn't exist. So condition 1 is not satisfied and this is not continuous. So there's our discontinuity. We knew that was going to happen. Okay, let's try one last one here. Now, yeah, I can see we can make this a discontinuity as well. We could factor it out. So this is going to be a removable discontinuity. So let me just show you. Now down here I can factor this out. Now this is the wrong way around, but we can fix that. We're going to put a negative out front, and that will make this x minus 3. Okay, so I can get rid of it. So 3 is a problem, but I can get rid of it. This means it's going to be a removable discontinuity. So you could also see that if you just wanted to go through the definition of continuous, if you put in 3 here, you're undefined. So that's no good. Now, if it's going to be removable discontinuity, from the left and the right, you're going to get the same value. Well, I've done those algebra tricks that we've learned in, I think, the last chat section. I can find the limit of this value when x is 3. It's going to be negative 3 plus 3 over 3. It's going to be negative 2. So this has a limit. It's negative 2. It's the same from the right and the left. So the problem is it doesn't meet condition 1. So I already showed you this is a discontinuity, but here's how we could prove it from the definition. Okay, now again, I know this is getting confusing for something very simple, but that's a little bit of what happens when we get to higher level math, where we have to have these precise definitions so that it's true all the time. And so continuity, just the simple idea that the line doesn't break, has to be put into very specific terms in order for us to prove it, and that's what we were doing here today.